Welcome to this fourth class about direct policy search and reinforcement learning. In this class, we will address the following question. Does the policy gradient perform better steps than direct policy search methods? First, a reminder about the context for this class. In the beginning of the playlist, we mentioned that deep reinforcement learning methods seem to be far more sample efficient than direct policy search method, and we are wondering why this is so. And we have seen a list of potential explanations. And in this video, we will address those two potential explanations. So first, the idea is the gradient gives the direction of steepest ascent, so it may improve faster. We will see that this is not the point. And we will see that the fact that gradient ascent does not need sampling and that it uses analytical knowledge of the function that it wants to optimize is not the key explanation either. And then on the next lesson, we will see the other potential explanations. So first, let's focus on the strength of the policy gradient approach. So in principle, the gradient ascent might be superior for two reasons. First, the gradient computation requires no sampling, and second, the gradient provides the best direction of improvement. Let me first show you the second point with some easy mathematical proof. So we have some parameter theta, and we want to find the change in theta, delta theta, that will increase the performance the most. Okay, we want to find the best direction to improve the performance. The best improvement is reached when the change in performance according to delta theta is null. That's always this good old idea that you reach an optimum where your derivative is equal to 0. So what we will do is that we will derive this expression with respect to delta theta, and we will take a first order approximation. So the first order approximation of this is g of theta plus the gradient of g of theta with respect to theta transpose times delta theta plus a term which is quadratic in delta theta plus either order terms. So this derivative is null when the derivative of this expression is null, and if you derive this expression, you get the gradient of g of theta transpose times this plus 2 times this term. And finally, if you want this term to be null, you have the best delta theta, so delta theta star is minus alpha, where alpha is some simplified expression for 1 over 2 mu here, times the gradient of g of theta. So the best direction of improvement is given by the gradient. This is what we wanted to prove. But we will see that in practice, we get an approximated gradient from sample trajectory. So this good theory is valid, but it's not true in the case where you are using a gradient coming from an estimation. The second point is this true that you don't need sampling when you are computing the policy gradient? It is true that when you are just applying a gradient, you are taking a mathematical derivative, so you don't need sampling. But the point is that in the policy gradient method, as we have seen in the policy search videos, the cost function g of theta is known through sampling. So we get this expression from the gradient, and we had to sample over state action pairs. So actually, we need to sample to compute this gradient, and then we can perform gradient ascent on this expression, and this will require no further sampling, but we had to sample just to get the general expression. Okay, so we need trajectories to perform policy gradient updates, and we also need trajectories to evaluate policies in direct policy search, so we should compare which of the two is the most efficient. Another point which is quite important is that when you are using PyTorch or TensorFlow or any other gradient computation library, you use in general adaptive or advanced gradient ascent techniques. For instance, you use ADAM or other mechanisms. There are many adaptive gradient ascent methods, ADAM, RMS-prop, Momentum, Nesterov, etc. There are also advanced gradient ascent methods such as the natural gradient, Gauss-Newton, some second-order gradient methods. But if you study all these methods closely, in fact, there is no free lunch. There is no technique that is better than all the rest, whatever the context. In practice, with neural network, ADAM often wins, but we can see that the best optimizer is problem dependent. For instance, if you want to apply reinforcement learning to many continuous control problems, there are times where using RMS-prop is better than using ADAM. To illustrate this idea that there is no free lunch, I took the example of momentum. So momentum is this idea that if you want to go down, your point here will collect some inertia, and the inertia will help it cross this local optimum to go better down here. So in a landscape like this one, having this inertia is good because you will fall up into a better minimum. But if your landscape is like this, the same inertia will drive you here, so it is in a worse optimum than before. So there are times where having inertia is good and times where having inertia is poor. And that's the case with all the gradient ascent techniques, that depending on the optimization landscape, they can be better or they can be worse, and there is no general winner. If you want to better understand those advanced techniques, you have this paper about adaptive gradient ascent techniques, and we've wrote this paper about advanced gradient descent technique. Let's now see two other limits of the policy gradient approach. The general idea is that a gradient provides a local direction and needs a step size, and it can be wrong about the direction, and you may also be wrong about the step size. So for instance, if your step size is too large, it may result in a loss rather than in an improvement. For instance, you are here, you are following the gradient, so you are going to a better performance, but you took a too large step and you just missed the optimum and you felt somewhere below here. On the other side, if your optimization landscape looks like this and you take the gradient, if your gradient is accurate, you will increase in the right direction. But given that your gradient is approximated, your direction could be slightly wrong, and this is enough to fall into some bad optimum rather than increasing your performance. So the general idea is that gradient descent techniques, they are blind. They just move from the current point to some direction, but the improvement depends a lot on the landscape. And the gradient step only ensures very local improvement. That's why you need, for a trust region, to avoid taking these too large steps and fall into bad local minima. By the way, the policy gradient is also inaccurate because it suffers from variance, as we have seen in the policy search video, due to sampling and due to the fact that it performs a sum over local gradients, as I have shown in the previous video. So you may have wrong direction of improvement, inaccurate step size, so using the policy gradient is not guaranteed to always improve your policy. And if you play with basic reinforcement learning algorithm, even with very simple environments like cartpole, etc., you will see that the performance does not increase monotonically. It goes up and down. On average, it goes up, which is what matters for us. But you cannot say that the gradient always improves your policy. Now let's have a look at the advantages of direct policy search. First advantage, which is very important, is that each time you generate a population, then you evaluate the solutions in your population, which means that your solutions are evaluated before being selected. So it means that, by contrast with policy gradient, where you move into a direction and you do it no matter if it's good or bad, here you first make sure that it's good and then you go towards better solution. That's a reason also why population-based methods do not need a trust region. They can evaluate a solution which is very far away from the current solution, and if it's good, they take it. Two, they can perform very large jump in the policy space. In particular, where you have some problems where you have a flat landscape, with a policy gradient, it can take a lot of time before you move outside the flat region. Whereas with a method like the cross-entropy method, you can perform a very large jump in just one step, and then you have a better policy and you move out of the flat region. Another point also is that by using a policy, they investigate more potential solutions at each step, which means that they can be better at finding good local optima. Another point is put forward in the paper of Tim Salimans that presented evolution strategies as competitive to reinforcement learning. What Salimans makes obvious is that in reinforcement learning, the variance accumulates along each individual action, so a longer trajectory will have more variance. Actually, using a discount factor helps, but whatever you do, if your trajectory is very long and if your system is stochastic, in principle you will have some variance. So in direct policy search methods, the variance does not grow with the left of the trajectory because you just consider a trajectory as a point. It's just a sample from which you will learn something. Whereas in policy gradient methods, you consider each state action pair independently, so you are very sensitive to this variance along trajectories. So direct policy search methods are in general more advantageous in problems with longer trajectories. Another point that comes from this paper from Lehman and colleagues is that an evolutionary strategy optimize an expectation of reward over a population, which makes them more robust. In fact, in policy gradient method, you have one point which is your current trajectory. You move according to some gradient, and if you fall into a very bad optimum, that's it, you are stuck into your bad optimum and it's very difficult to recover. Whereas in direct policy search methods, you keep several solutions. So if one solution gets bad, that's not a big deal because you can still rely on the other solutions to improve. Another point also is that direct policy search methods do not depend on Markov property. They are more general, they can address POM-DPs, etc. I have shown in the second video of the policy search playlist that when you are using the policy gradient, you rely a lot on the Markov property because at some point you are computing the probability of the trajectory as a product of the probability of individual steps, and using this product means you consider the steps as independent of each other, which means that you need Markov property. That's not the case in evolutionary methods because again you consider a trajectory as a single point and you don't care whether the way you performed on your trajectory was based on partial observation or not. Finally, evolutionary strategies do not need the policy function to be differentiable, okay? They are derivative free. So you can have a policy which is completely discontinuous. Of course, most of the time we use neural networks which are continuous, so this does not matter, but you can apply evolutionary strategies to more exotic policy functions. The bad point about direct policy search methods is that Nesterov, in this paper, has shown that derivative-free approaches need more iterations than derivative-based approaches. So the gradient step leverage the knowledge of the policy structure to be more efficient in a number of iterations. And as we will see in the next lesson, the fact that it works on separate state action pairs rather than just trajectory is very important. And that's it for this lesson. Thanks for listening.